All righty, day 3 of section 2. We're just really slowing this down for you guys. All right, so let's talk a little bit more about limit theorems. Do you remember a continuous function? In layman's terms, it's like, if can you draw it and not lift up your pencil, right? Can you draw the graph? If a graph is continuous, can you draw it and not lift up your pencil? Are there no holes, right? That was a continuous function. But now I'm going to give you a more formal definition in order to show that a function is continuous at a specific point. So a function f of x is continuous at x equals c, so at an actual x value, IFF. Remember, that means if and only if. It's not a typo. Um, there's 3 parts to this definition. And the first one is that f of x is actually defined at x equals c. So like, let's say the c is a 2. So at x equals 2, can you look at the function and go f of 2? Is there a closed dot representing f of 2, that there's an actual y value that exists for your x value? Does the limit exist? So remember, the limit exists as long as the limit from the left and the limit from the right, if those are the same value, then we say the limit exists at x equals c. And then the third part is that the first 2 are the same value, so that this limit that exists is exactly equal to the function's value at that same spot. So all 3 of these need to be true if a function is continuous at a specific point. It turns out that polynomial functions are like x squared and x cubed and x to the fifth, and you can have a bunch of like 4x to the fifth plus 3x to the fourth plus 2x cubed, blah, 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 blah. All of those are polynomial functions, and they are continuous for all real numbers, for all of them. Rational functions, though, if you're dividing by 0, you got an issue. Anyway, so, all right, so let's look at an example. We're going to determine if the function is continuous for all real values of x. And then if not, indicate which condition of the definition failed. So this is a piecewise function. This is what's most common when we're asking you about continuity and limits and things like that. And if there is an issue, it will show up. Notice that we're giving you different definitions for different pieces. That's why it's called a piecewise graph, right? There's little pieces of the graph, and where the values are changing are all at x equals -1. So if there is an issue, it's going to happen when x is -1, because we're changing what the function's defined as for each of those guys. All right, so what you're going to do is graph it. Yeah. Do you remember that y equals x squared plus 2 is a parabola opening up? And instead of the vertex being at the origin, it'll be shifted up 2. Now, we are only going to graph the portion of the parabola that is less than, there's no or equal to sign underneath there, so it'll be an open dot at -1. So you could do a table, or you could draw the full parabola would have went down here, and the vertex would have been right there at 0, 2, and it would have come back up and done this. But it's only defined for when x is less than -1, which is why I've got an open dot right there, and then it's just to the left. Y is equal to 1 when x equals -1. All right, well, that's the point. When x is -1, y is 1. Put a dot right there. And then y is equal to 2x when x is -1. Well, y equals 2x is a line, it's a straight line, that goes to the origin and has a slope of 2. So it's like this graph here, but we only want the part that's x is greater than -1. So when x is -1, you would be here at -2 for your y value. You'd put an open dot there, and then it is a straight line with a slope 2 going that way. Okay, so there's the graph. There's your graph of your piecewise function. So definitely start off by graphing it. And then we want to see, is it continuous, right? For all values. And if it's not continuous, obviously you can see, I don't know, layman's terms, you can look at this and go, oh yeah, I would totally have to pick up my pencil. So it's not going to be continuous at -1, but we have to use the definition. So first of all, is the function defined at -1? And it is, because there is a closed dot. Without, if they wouldn't have given this middle line right here, if that middle line was missing, then f of -1 is not defined, because at -1 you've got an open dot here and you've got an open dot there. It's defined when it's a closed dot, right? So we needed that second line of y is equal to 1 when x is -1 for f of -1 to be defined. And it is, f of -1 is 1. You can identify an actual y value with a closed dot. Then we want, how about the limit? What about the limit as x approaches -1? Well, you got to look at the two-sided limits to see if the limit exists. So from the left, as x approaches -1 from the left, you're on this part of the graph. And what is your y value? 3. As x approaches -1 from the right, you've got a y value of -2. And so the limit as x approaches -1 does not exist, because from the left, it's equal to 3, but from the right, it's equal to -2. And for the limit to exist, these two values would need to equal each other. And so the limit does not exist, which means it's not continuous. There you go. You can have ones where it's defined, that the limit exists, but then yet if these two guys didn't match, then it could fail continuity that way also. So yeah. Anyway. All right. Here is your homework. I hope you all are having a fantabulous day. Yes? Yes. Maybe I can figure out how to stop this video. This is like the worst part, right? Okay, bye.